Hello! In this video, we'll be tackling a problem that might look intimidating at first glance. We're going to learn how to solve the fourth degree polynomial equation, x to the power of 4 minus 4x cubed plus 6x squared minus 4x plus 1 equals 0. By the end of this lesson, you will be able to recognize special patterns in polynomial equations and use them to find all the solutions. So, our main goal is to find all the values of x that make this equation true. In other words, we want to find its roots. Let's begin by observing the coefficients of our polynomial. Here's our equation again. Notice the numbers that multiply each power of x. The coefficients are 1, minus 4, 6, minus 4, and 1. Do you see a pattern here? The coefficients are the same if you read them forwards or backwards. This type of polynomial is called a reciprocal equation. So, we're dealing with a special kind of polynomial called a reciprocal equation. This pattern is our biggest hint on how to proceed. A key property of these equations is that if a is a root, then 1a is also a root. This gives us a special property. If we find one root, say a, we automatically know that its reciprocal, 1 over a, is also a root. Now, what's a good first guess for a root? The rational root theorem tells us to check divisors of the constant term. The constant term is 1, and its divisors are plus or minus 1. Let's try x equals 1. It works! 1 4 plus 6 minus 4 plus 1 equals 0. This confirms that x equals 1 is a root. And since it's a reciprocal equation, its reciprocal, 1 divided by 1, which is also 1, must also be a root. This strongly suggests that x equals 1 is a root with a multiplicity of at least 2. In other words, the term x1 is a factor at least twice. So, our analysis tells us that x equals 1 is a root of this polynomial. Now that we know x equals 1 is a root with a high multiplicity, we can use a more powerful algebraic identity to solve this equation. Recall the binomial expansion theorem. The expansion of a plus b raised to the power of n is given by this formula involving binomial coefficients. The binomial coefficients, represented by c, n, k, are the numbers in Pascal's triangle. For n equals 4, the fourth row of Pascal's triangle contains the coefficients 1, 4, 6, 4, 1. Wait a minute. These are the absolute values of the coefficients in our original polynomial. This isn't a coincidence. It's a key observation that unlocks the solution. Our polynomial alternates in sign. The terms are positive, negative, positive, negative, positive. This sign pattern is exactly what you get when you expand the binomial x minus 1 raised to the power of 4. Let's expand it. c, 4, 0, times x to the fourth times negative 1 to the 0 plus c, 4, 1 times x cubed times negative 1 to the first, and so on. Calculating the coefficients and signs, we get 1 times x to the fourth minus 4 times x cubed plus 6 times x squared minus 4 times x plus 1. Compare this to our original polynomial. They are identical. This incredible pattern matching reveals the polynomial's true identity. So, our problem has been transformed. Instead of solving a complex fourth-degree equation, we're now solving something much simpler. We need to find the values of x for which x minus 1 raised to the power of 4 equals 0. How can a number raised to the fourth power be 0? The only way this can happen is if the base itself is 0. For the fourth power to be 0, the term inside the parentheses must be 0. So, x minus 1 must equal 0. This gives us a straightforward linear equation. To solve for x, we just add 1 to both sides. And we find our solution. X equals 1. But is that the complete answer? According to the fundamental theorem of algebra, a fourth-degree polynomial should have 4 roots, counting multiplicity. Our solution, x minus 1 equals 0, explicitly shows that the factor x minus 1 appears 4 times. This means x equals 1 is a root with a multiplicity of 4. This means x equals 1 is not just a solution, it's a solution that counts 4 times. A root with multiplicity is a value that solves the equation multiple times. Visually, if you were to graph this function, you would see that the graph touches the x-axis at x equals 1 and bounces back, rather than crossing through it. Here's what that graph would look like. It perfectly touches the x-axis at the point 1, 0. Let's quickly review the elegant path we took to solve this seemingly difficult equation. Our objective was to solve x to the fourth minus 4x cubed plus 6x squared minus 4x plus 1 equals 0. Here's our final answer. X equals 1 with a multiplicity of 4. The first crucial step was to recognize the pattern in the coefficients and identify the equation as a reciprocal polynomial. This pattern also hinted at a connection to binomial expansion. The second key insight was to notice that these coefficients perfectly matched the fourth row of Pascal's triangle, but with alternating signs. This led us to identify the polynomial as the expansion of x minus 1 to the power of 4. By making this connection, we were able to factor the entire polynomial. This transformation simplified the problem immensely, allowing us to find the single solution, x equals 1, with its full multiplicity of 4. The lesson here is to always be on the lookout for patterns. They can turn a complicated algebra problem into a much simpler one. Thank you for watching.